Lake is home to two very large sinkholes and one that has at least doubled since it first arrived in the 90s.
The smaller one, this is the initial sinkhole that happened in the 80s. This one here is the most recent one in the 90s. Back then, like I said, we could throw a rock across it and go on the other side. But now it's so big and you can't hit a golf ball across it. It's over 400 yards wide.
Mitchell fears these sinkholes may just be the beginning, and he's expecting more to pop up around the area with all the recent activity. Reporting live in the studio, Haley Brooks, Local 2 News. Haley, thank you.
Hey YouTubers, that was a clip of some sinkholes in the state of Texas. I find that very startling that we are, this is caused probably from fracking of oil. And oil is such a primitive source of fuel. I mean, why are we still on the oil? We're destroying our own habitat by drilling into our own planet. Our Earth is very much alive, just as much as we are, and we're over here poking holes in her. I mean, how would you feel if somebody came along and poked holes in you and sucked your life force out of you? I find it very, very disturbing, and I think it's wrong. And I mean, we have the capabilities of building vehicles with batteries, rechargeable batteries, as power supplies, and DC motors, and maybe some solar panels on the top. I mean, really, as a civilization, we need to advance just a little bit better than what we're doing. So I know we've got Tesla vehicles and different kinds of electric vehicles, but we're just not quite there yet, and we should have been there like yesterday. All right, so let's move on. I just had a rant a little bit there, but this is a circuit. It's the same circuit I've been showing if you haven't noticed, for the last few videos, and there's a reason for this. I've been doing this for well over 20 years, and I find that this circuit has everything that is needed to show excess energy in a collapsing magnetic field. A lot of the times, for those of us who have been pulsing coils for years on end, and then catching the resulting collapsing field with diodes into a capacitor or into a load or whatever. The thing about diodes is it's very difficult to see the excess energy in a collapsing magnetic field, so it's very easy for one to say, hey, collapsing magnetic fields are never ever going to be over 100% efficiency electrically. They might say they'll probably most of the time just end up with like an 84% electrical efficiency, and and the diodes is what's killing the small little excess energy to where you can't see it. If you've been playing around with electronics long enough, you'll understand that there's a voltage drop across a diode and some resistance, and so there's a slight power loss through a diode, and it's that slight power loss that we need to see in order to see something above 100%. Okay, so this is going to be a comparison between a direct connection from our battery or power supply into our load right here, and comparing that to Tesla's impulse DC technology. And so let's do that right now. Here, let me get a zoomed out view here of everything, and later on also I'll show the schematic and have a little bit of a better explanation for what is going on in this seemingly simple circuit. And so here's the power supply running our switching work. We are not concerned with that, because that's just the power needed to do our high frequency switching. What we are concerned with is, and what we're looking at is the power from our battery being pulsed into our load. That's what we're looking at. All right, so now right now we got a direct connection. I've added a few more components since last time. They're not major changes, but we got a capacitor on the input, and that white wire right there is a switch, so we can disconnect the battery and let the energy in the capacitor run into through our switching circuit and into our load. And that's what our comparison is going to be. So right now, if we follow that black wire, it's connected through that white wire to it's in parallel with the battery. And if we follow that black wire around, it's going immediately into our meter measuring input current. Right now it's off. And then that red probe right there is going directly into that green wire, which is going directly into our load, which is in parallel with the capacitor. There's the load, it's in parallel with our capacitor on those yellow wires. And then of course we got our meter reading current going directly into the load with that yellow wire right there. So let me turn that on right quick. And so right now this is just a 100% transfer of energy, not electrical efficiency, just a 100% transfer efficiency. So whatever is leaving the battery is going directly into our load at an exact 100% transfer of energy. And as you can see, the currents are exactly the same, of course, because it's the same current coming out of the battery and as what's going into our load, of course. And the voltages are exactly the same as well. So this is a 100% transfer of efficiency. Now, we're going to disconnect our battery and let the input become the capacitor, the energy coming from the capacitor. So let's do that. And when we do that, we're going to observe what is happening to our volts in our capacitors. So both capacitors will drain into our load. And that's what we'll be seeing. So let's do that right now. So we'll just disconnect it from the battery. So now look, they are both draining at the exact same time, at the exact same rate. Current we're not so concerned with right now. The current is lower because this capacitor is compensating the energy into our load, and it's kind of pushing our input current back, but that doesn't matter. What matters is this energy and both capacitors draining into the same load, okay? And as you can see, it's the same. So this is the energy in both the input and output capacitors. So let's connect this back up and recharge our capacitor here on the input. And that's just the current charging back into the input. Now, the thing about this is you're not going to see, you're not going to be able to see a capacitor discharging its energy and getting more energy into the output capacitor, because it just doesn't work like that. The current has to be constant. Okay, so this is why we have to, when we go run it, when we replace our battery with our capacitor, then what we're seeing is what the battery was doing immediately prior to disconnecting it and letting it run from the capacitor. So now let's use Tesla's DC impulse technology. We'll turn that on over here. So that's just the charging of the capacitor. And like I said, charging and discharging leads to nowhere, okay? But if it's constant like this, then you'll see now the current, of course, again, are the same, but now look at our output voltage. It is much higher, okay? So the watts is going into our load is higher than our input watts. Now, let's disconnect our capacitor again, our battery, and let it run. And what this shows is both capacitors are now draining into our load. So this capacitor and this capacitor are draining both into our load. And as you can see, the output energy in our output capacitor always remains higher. So this is just to show the energy, or what was going on just before connecting it from the battery, and what the battery was doing, and the watts that was happening just before we disconnected the battery. And as you can see, it's got the exact same rate pretty much. The currents again are pretty much exactly the same. It's draining. And so the voltage across this capacitor is always higher, therefore the watts in our load is always higher. So the diodes take away our energy, and as you notice, there is no diode coming off of our coil over here. And so the 100% energy, here, let me connect this back up. So the load is taking 100% of the energy from our battery, and then the coil is returning just a little bit more onto our load. And having no diodes allows us to see this. Now, a word on collapsing fields. For those of us who have been experimenting with pulsing coils and catching the resulting collapsing field with a diode, and either charging a battery or a capacitor or just directly running some kind of load, most of the time will always be like 84% electrical efficiency or so. But we would like to consider the output, the collapsing magnetic field, as an output. But why? Why are we doing that when the collapsing field is just the energy that came from the power supply, which in this case is a battery? It's just the energy that's going in and temporarily being stored in the magnetic field and then coming back out. So I believe we should be considering that output from our coil, from the inductive discharge or the collapsing field, as just input. So we're losing energy through the resistance of the coil onto our load. Okay, and so we'll never see anything more than 100%. You're better off directly connecting the load to the battery and getting the input directly. At least then we have a 100% transfer of energy. But knowing that the input is like 100% of the energy being transferred into our load, and then our coil is also giving back a little bit of energy, then we have to ask, where exactly is this little bit of excess energy coming from? So there's more coming out than what's going in. So let's move on to the schematic now, and so we can explain this a little bit better. Let's do that right now. Okay, so here's the schematic. Everything pretty much remains the same, except I changed out the C1 capacitor right here from a 0.01 microfarad film capacitor to a 0.02 microfarad capacitor. And the only thing else we've added is the capacitor in parallel with the battery right here with a switch. So we can disconnect the battery and then letting the capacitor power the circuit. The point of the capacitors C3 and C4 is to show the energy levels on our input and our output just before we disconnect it from the battery, to show what the battery and the constant current coming from the battery was doing with the energy levels here on our output and input. The output C3, of course, is having more, it has a higher voltage, therefore there are more joules of energy, energy in the form of joules, powering our R5 load resistor with more wattage than the input. But since we disconnect at the switch here our battery and basically connect into our circuit this capacitor, then both capacitors drain into our load. So the negative is, of course, is going into our load here like that, and starting from this negative of this capacitor is also going into our load like this. There's also a meter right here that I inserted to show current coming from our power supply or capacitor into the R5 load. So this is why the meters are showing the same current, because it's in the same path of the current. But this meter is showing the current directly after our power supply negative, and this meter is showing the current directly before our load resistor. So this is a conventional way of reading power coming out of our power supply and going into our load, of course. But the load is showing more. What's happening is that the load is not only getting our 100% transfer of energy from our power supply, okay, but the collapsing magnetic field is adding its own little bit of energy as well. So the output of our R5 load resistor has more watts than what is being supplied by the input alone from our power supply. Notice there is no diode. Okay, so the switching is fast enough on our MOSFET to let the collapsing magnetic field go ahead and power our resistor, but it's not going to go backwards because, well, it's off and disconnected. So it's acting sort of like a diode. The MOSFET is a very good switch in that it acts more like a Tesla spark gap. It cuts the current off very well, and then the resulting collapsing magnetic field from the coil is collected in the capacitor and output load of our R5 resistor, which is in parallel with the voltage across our capacitor to show the true voltage in our load, which is consequently receiving more joules of energy than what's coming out of our input. So this is a good way, I believe, that if you don't have an oscilloscope, you can look at our energy levels by looking at the energy levels in our capacitors. But by all means, use oscilloscopes if you do choose to replicate this, which I do strongly suggest and would like you to replicate. I would like you to replicate this and then post back your results. I would like to have more people doing this than just me, to help show exactly and more accurately what's going on. I do believe the meters are reading pretty accurately, but most of all, the capacitors are showing us the energy levels of our input and output just prior before the battery disconnection. So that's it for now, and please replicate this. And also, if you're new to the channel, please subscribe, and please like and share as usual. And that's it for now, and thanks for watching, and I'll see you on the next video. Have a good one.